Yelling at me again. Oh, Twitch. What am I doing wrong? Let's see. Telling me something's wrong here. Trying to figure out what it is. I'm gonna have to deal with some ads real quick while I figure this out. Oh.
Yesterday too, you know. Now we just wanna go back again. And I can't help thinking about that feeling. Here where we wanna be. Different vicinity. Now it's clear we can do whatever 'cause you're right here. Here where we wanna be.
Oh, excuse me. Have a little bit more setup to finish here, and then we'll get the video changed over so y'all can see what I'm doing here. Just a moment, please. I'll turn down the music a little bit for now. Alrighty. Hello, everyone. Hello. Good afternoon. Well, it's afternoon here. I don't know about all you, but... Hello. We are going to be working on making a... Well, really, this is just for learning basics of emulation in Rust here. We're going to be working on making a Chip 8 emulator. If you don't know, Chip 8 is well regarded as the like Hello World project for emulation. So if you want to do other stuff with making an emulator, doing something with Chip 8 kind of lets you dip your toes in the water and kind of figure out how things work. I decided to do this because recently someone offered to work on a project together to make another kind of emulator, but because I am still very new to Rust and want to make sure that I am at least somewhat familiar with things before diving headfirst into that, this is what we're doing. So welcome to the stream. Thank you for stopping by, and we'll be getting started here. Let me know if the music is too loud or not loud enough or whatever. I do have the little player in the bottom right if you want to see what the music is at any point. It's by Hyper Potions. They allow some of their music to be streamed on Twitch as long as we give them credit. So I just have that down there so that we know what the song is and who it's by. And yeah, I guess we'll be getting started here. I'm going to be going through a little book. I will... Yeah, can I find this real quick? If anyone for any reason wants to know exactly what I'm doing, the emulator... The specific book I'm using here can be found here. And without further ado, we will begin. I'm going to be reading through this. I don't have the book up on stream. When I was looking at it through some testing, the text does not come through well. The text in the actual PDF is serifed font, unfortunately, and I don't feel like rebuilding the PDF or trying to edit it right now to fix that. So I'm not going to be streaming the PDF itself because it's basically unreadable after compression. It's almost unreadable for me. But we make do. Anyways, welcome everyone. Welcome. Happy to have you all here. Alrighty, so we have our basic directory set up here. We have our actual desktop application. We have our little library project here as well. And that's where the module is going to be where most of the emulation backend goes. This should take us through basically making the Chip 8 emulator from start to finish. I don't expect it to take too long, but we'll see. Yeah. So first, the most fundamental part of any emulator is, or any system, is the CPU. So we're going to begin there. For the time being, we're mostly going to be in our Chip 8 core backend here in this lib.rs file, our lovely little library file here. Well, we're ignoring all this for right now, just don't worry about it. Actually, I'm just gonna delete that for now. So, emulation is basically executing a program written for a different system. It's basically like executing a normal program, except we need to make sure that, like, we're basically manually implementing the CPU opcodes and everything here. And how the CPU actually works, like fetching the instruction, decoding it, and executing it. So we're just rewriting basically what the CPU on a chip 8 would do, but to run on a modern system. That's how most emulators work. Basically, obviously, I'm not the best person to explain all this, but you know, that's kind of how things work. So I'm gonna create a structure here. This is gonna be the main object for our backend, and basically is going to need to handle running the actual game, and we'll need to pass the information back and forth from the front end, like what's on the screen, buttons that are being pushed, etc. So we're going to create a few data items inside this here. This PC is basically a program counter. It's just keeping an index of the current instruction of basically where we are in the run. It's gonna get stored here, and it's that way it can be easily fetched, and you know the index will increment through the game as it runs, and can be modified manually with certain instructions, such as like jumping to different sections of the code, etc. I'm not going to explain every little concept here. It's a little hard because, like I said, I am going through this for the first time myself. But if anyone has any questions at any point, please let me know. I will do my best to answer questions that I can. I just don't expect me to answer or be able to answer everything. And we're also going to want to make sure we have RAM here. So we'll add a const. And it should have 4 kilobytes of RAM. Well, chip 8 was never actually a physical system, so it technically doesn't have, there's no standard for how much memory it has, but it was made to run on systems with 4 kilobytes, basically. So that's what we're gonna do here, make it simpler for ourselves. Some stuff in the UI around here so we work a little easier. I really need a third monitor, make things a little easier for me. So, like I said, everything in this struct is going to have basically everything our emulator needs. So we need to make sure that it knows how much RAM it has. Also, I'm not really liking these colors here. Can we change this? Not a fan of that either. Let's see here. That's horrifying. I should have definitely had a theme ready to go before we started doing this. I was using that one you saw me using at the start, but it is, I have some issues with how it looks lately. Let's see. It's too green. No, that's not what I wanted. Sorry that you're all... Get out of here. Sorry that you're all watching this. Me fiddle with this right now. I need this to not drive me insane at the moment. That's very red. Oh no. You'll have to excuse how scuffed this is at the moment. This'll work. This'll work for now. I'm fine with these colors. I'll settle on something that... this is like really bad contrast, though. I don't actually love how that looks. That just doesn't have good highlighting. We'll deal with these colors for now. Still don't like coloring here being barely any lighter than the background, but I hate this one the least out of everything I've seen so far. Okay, moving on. We now know how much RAM we need. And the chip 8 uses a 64 by 32 monochrome display, so it's 1 bit per pixel. So we are going to add a couple new constants here that need to be public because they need to be accessible by the front end. Ignore my inability to type. I never learned proper touch typing, so I don't have the best typing speed. I don't have to hunt for keys and peck them. I kind of have my own method, more or less, that's worked for me over the years, but I can't do the normal home row touch type on a QWERTY keyboard. It's just a little too hard for me. We have these here, and now, because these are only 1 byte, because it's a monochrome display, we can store every pixel, basically, as an array of booleans. Which sounds insane, I know, but it is what it is. Oops. Come on. Isn't that lovely? My, oh my, that's horrifying to me in some way. Oh, thank you for the hydrate. Thank you for the head pat. Nothing feels better than a nice head pat. Alrighty, let's see here. So, we have our program counter, our RAM, and our screen, the display. Next, we are going to work on adding the V registers. Because, believe it or not, RAM access is considered fairly slow, at least in this case. Much faster than reading from the disk, but still slow. So the CPU, most CPUs usually have registers. The chip 8 has 16 registers, which the game can use as it needs for faster operation. These are V registers and are basically going to be numbered in hex from V0 to VF, hex being base 16. So the author of this guide says they're not sure what V stands for, and I don't feel like going to look it up myself. So if someone wants to go find out what the V in V register means, that would be great. I have a feeling it just is the naming convention and it doesn't mean anything. And basically we're just going to group these into an array in our MU struct here. No, 16. What am I doing? There's 16 of them. We just talked about this, and we're going to add those to our struct as well. All right. And there's going to be another 16-bit register known as the I register, which is used for indexing into RAM for reads and writes. Well, the book gets into the more of this later on. For now, we just need to make sure we have it here. So that's what we're adding. Alrighty. Turn down the music just a bit. It was a little loud for me. I don't know how it is on stream, but I want to be comfy. Nice and comfy. Alrighty, so we have our registers, our RAM, our screen, our counter. And we're going to be moving on and creating a stack pointer. This is the Chip 8 CPU has a pretty small stack. It's an array of 16-bit values that the CPU can just read or write to. It's last in, first out, like most stacks. Think of it like a stack of pancakes. Very fun. Take pancakes from the top. If you take a pancake from the middle of the stack, I don't know what to tell you. Just stop going against the metaphor. I can't stop you. I mean, I can. I know where you live. In my apartment. You'll bite? Oh no. Oh no. Alright. The stack's basically going to be here whenever we're entering or exiting a subroutine. It's going to know basically where we started so we can return after the routine ends. Chip 8 doesn't say how many numbers the stack can hold, but 16 is a typical number here, so that's what we're going to be using, it looks like. In this case, the author does state that there are a few different ways to implement the stack. The easiest would probably be to use something in the standard library. There's standard collections and then I don't know how to say that. It would basically be, it would look like this, though. I put this up top here. But we are not going to... Oh, it's a double... Okay. It's a Q. Double Q. What a weird name. Anyways, we could use this, but this works for desktop-only builds. And a lot of things in the standard library don't work for WebAssembly builds. This specific guide is to make this work on both desktop and WebAssembly. So we are going to follow what the guide says. Again, just so we can get some experience with how these things are normally done. It gives us a better starting point when working on other things. Obviously, knowing that this is in the standard library, we could look into that for other projects if we are only targeting desktop builds. So instead, we're going to add yet another constant here for the stack size. Which, like we said before, is 16 again here. And we want both our, in the emu struct here, we're going to want the stack pointer and the actual stack itself here. Oh, it needs to be a semicolon. There we go. Alrighty. So, let's see here. We have our stack here, or obviously none of this is implemented yet. We're just basically getting all the data items created. This is actually reminds me a lot of how I would write out a COBOL program, starting with basically creating all of the data structures I need for the most part for everything, and then writing all the logic to actually do the work. This makes this a lot easier for me to comprehend, coming from someone who doesn't really know Rust but knows another language, where typically you just start with writing out all your data items. That might be the normal way to do programming. I don't know. I never took comp sci, or I should say I never really obtained any college credits other than English composition through an equivalency test, because I refused to actually take those classes. Anyways, we're going to continue on here. There's a couple other special registers that Chip 8 uses, it looks like. Mostly for timers. We're going to have a delay timer, which is just a typical timer, counts down every cycle and performing an action if it hits 0. And a sound timer. The sound timer counts down every clock cycle, but when it hits 0, it's going to emit a noise. Setting the sound timer to 0 is the only way to emit audio on the Chip 8. That's interesting design. So it looks like anytime we're going to want this to emit sound, we just set the sound timer to 0. Interesting. Alrighty. These are both 8-bit registers, and we need to have them both supported here. I believe we have everything here. Interestingly, I'm seeing something that wasn't in the book that hasn't quite come up yet, but we're going to just add it. It could have just been missed by the author, but I do see some in their next code. Something called num keys here. They didn't actually talk about. Keys down here. Unless I missed something, this was not already mentioned. Ooh. Yeah, interesting. I don't see this at all in our little book here, so I'm not sure what those are being used for. We'll worry about that later. So, DT is going to be our delay timer. That needs to be a comma. And ST will be our sound timer. I'm not a huge fan of naming variables like this, but I do understand why you don't want super long names, or because these are items in a struct and we don't want to have everything when we're writing all this out be extremely long. If I was writing this myself, I'd probably try and make these a little, or at least comment it to explain what the different parts are. For this, we're just going to leave it as is so we can follow along with what the book has. And for this struct here, we are going to add new constant here for our starting address. There we go, and we are going to write the implementation for this. We're basically writing a constructor here. I'm not a fan of these colors. I don't like this highlighting where it's just this gray. I'm not a huge fan of that, but whatever. I wonder, can I just get VS Code to automatically implement all of this here? Yeah, look at that. False is going to make our screen black. Again, as we talked about before, the screen's monochrome, so we're storing the pixel values as booleans. So false is just going to be black, like there's no color or no pixel there being displayed. Zero, zero. We're just setting our starting values here, basically, when we call the constructor. Well, that's not what we wanted. Zero and zero. There we go. It's going to yell at me right now. Don't worry about this. This is just yelling at us that all of these fields are never read. Can I actually just ignore that for right now, please? I shouldn't have saved it. I'll actually learn how to properly use VS Code at some point, don't worry. Not today. We'll deal with the squigglies for now. Alright, so basically this is just initializing all our values and arrays to 0, except for our program counter, which gets set to this value here, which is just 512 in decimal. Wherever it was. Program counter. Yeah, right here. Because the start address here, and we have that set up here. The emulator has to know where the beginning of the program is, and the chip 8 standard is that all chip 8 programs will be loaded starting in that RAM address right there. So the number will come up again, so we've defined it as a constant. So that's the beginning of the part. This is basically the structure of our emulator here, and we're going to implement the actual methods here. The next thing we're going to do is add a push and pop function for the CPU stack. I do believe these are like part of the standard library now. There's ways to do it that way. Again, we're just going to do what's written in the book here to make it work. As they show, there's probably functionality reasons for this. I couldn't give you exact reasons. I'm not too familiar with it myself. We are learning together. Or it's just me. I'm not sure. If I can learn to type today. So push is going to just take a mutable reference. This is to push something onto the stack. And we will increment stack pointer. Nice and easy. So basically we take whatever gets passed to the push here, it gets put onto the stack into the array. And then we increment the stack pointer. Very simple. Very, very simple. And now we are going to add a way to pop something off the stack, because we need to be able to do that. Again, we want a mutable reference here. And this will first will decrement the counter because we want it, because if push always increments, it's going to be on something that has no value right now, and if we try and pop something there, it will panic, because it's basically we're trying to pop an empty part of the stack. We could write something to handle that, but that should never happen, so we should panic really if it were to happen. Panicking here is fine. Okie dokie. So we have our push and pop for our stack here. Fine. Once again, going to yell at me that these are never used. We are not worrying about these right now. I'll just leave this up here so I'm not staring at all these right now. Following the book, we're not going to really run into compiler errors, at least we shouldn't, unless something has changed significantly since this was written, and if that comes up, then we'll have a fun time trying to figure out what needs to be changed so that we can get this to compile and work properly. Alrighty, so we have our push and pop to add to the stack pointer, pop things off the stack, perfectly fine. Now we need to dive into how the chip 8 display works. Basically, from what I'm reading here, it renders sprites that are stored in memory onto the screen one line at a time. So the game developer, whoever develops something for chip 8, needs to correctly load their sprites before copying them over. And, the system can also have like standard sprites for commonly used things as well. So the first 512 bytes here are completely empty. Bytes or bits? Oh my god, my brain's not working. Hi. Welcome to the stream. So our counter started here. This is where all the chip 8 actual programs start. So we have the first 512 here addresses to use, basically address space, which is great because that means we can store sprite data for font characters for all of the hexadecimal digits, so 0 through 9 and A through F. We could, in theory, store this at any fixed position in the RAM, but this is empty anyways, so... So because each character is made up of 8 rows of 5 pixels, each row uses a byte, that means each letter takes up 5 bytes of data. Let's see here. I wonder if I can quickly add this in here so y'all can see what I'm talking about. Bear with me a moment. I wanna get this on screen so people can see exactly what I'm talking about here, so it's a little less confusing. Just a moment, please. There we are. Oh my gosh. Okay, here we go. Just so y'all can see what I'm looking at here. This is how... This is what we're looking at for how basically the sprites are stored. It's just, as we talked about, it's a monochrome display, so the zeros are black pixels, and the ones are going to be our monochrome, in this case white, for all of these. So this is what it looks like. Nice and simple, pretty easy to understand, honestly. So these are all encoded into binary here. Because every sprite's 8 pixels wide, that means each row needs 8 bits, which is 1 byte. So 5 bytes total. Very simple. Let me get this back off the screen so we can... Oh, go back to... So everyone can see the whole thing now. There we go. Hope that kind of explained why we're doing things the way we are. So, now all we have to do is define the arrays of the bytes so that we know we have our font set, basically. I'm going to go all the way back up here and add a couple more fonts here. And just so I'm not typing this all out by hand, because I think I'd go a little insane typing all the hex values out right this moment, we are just going to copy paste this in here. So this might look a little confusing at first glance, but these hex values here are just literals for the binary values that give us the exact representations of each of these. So for each row, so you can see we have the 5 here. These are all and the binary value of each of these bytes is going to be what we saw before for each of these, so we get the actual characters here, the hexadecimal characters we need. Ooh. Okay, so now that we have that, we're going to actually need these loaded into RAM when we initialize this. So we're going to go back to our new implementation here, and we are going to modify this a little bit. This should now say, what I can tell, self. There you go. Keep the rest of this. And all this is fine here at our semicolon there that we were missing. And then here, we will load our array into RAM. All right. So this initializes our MU object here in the same way as before, but it's copying in the character sprite data into RAM before returning it, which is what we want here. We're also going to want to be able to reset the emulator without creating a new object here. So we're just going to reset everything back to their original values. So write that here. And we have our default values here anyways, so this is fine. And how do you do this? That's what we wanted. There we go. Okay, perfect. This also needs to be there. Change all of these here to That's not what we want. Okay. One of these days I'll actually learn the shortcuts properly here. We're basically just setting all of these back to 0 here. Or to their initial values. I swear there's an easier way to do it than this, but we are doing it how the guide has written, and I could have just copy and pasted what they had, but it's fine. There we go. And we want this here. Perfect. Now we have a reset function, so when we want to go back to basically our what it should be when we first start it. That's all right. I don't need to explain why we have this, I don't think, to the people watching. I think that's fairly self-explanatory. We have this, so it's a reset. We've made it so it resets back to their initial values. That's that simple. Okay. Next, we need to define how the CPU will process each instruction and move through the game. Basically, we're going to deal with ticks here. Going to do that under these. Gonna add some comments here like they have in the book that are going to be for the different sections of what this needs to do. So right here we just have fetch written out here. And now we want to have our fetch function that we're going to be using for all of the opcodes. Okay, so this is how things are going to be for now. Don't worry about it. We will write out the body of this in a moment. Hi, Oracle Writer. Welcome to the stream. Welcome. Hydrate, thank you for the reminder. I very often get sidetracked and forget to drink enough water. Ignore the errors here. These will no longer be a problem once we actually write out the bodies of these functions. You ask about my current experience, if that's okay? Sure. I mean, you can ask me about whatever. I'll do my best to answer. I can't promise that I'll give you the best explanations, but I will try to answer to the best of my ability. I need to put on some different music. I'm going to make OBS not output this to the VOD track anymore, and I'm just gonna put on music I actually want to listen to. Well, not that I don't want to listen to this, I just different comfy music, but I don't want the VODs to have problems, so we'll have to whoever watches the VODs later will just have to deal with it being silent, and that's fine. Change the track mixing here. Looking for some answers for personal growth? Yeah, sure. Feel free to ask me anything. I'm currently fiddling with my music anyways, so. Alrighty. While I wait for questions from Oracle here, we'll go back to what we were doing. Oh, that I worked infrastructure for some companies. What does that mean? Not infrastructure. I do mainframe programming. I basically work on legacy COBOL applications. I don't. If someone told you they worked infrastructure, I doubt it was me. Um, I do COBOL programming on a mainframe. Basically, mainframes are just supercomputers, kind of. It's a very simple way to explain them. They're very good at certain types of math and they do it very quickly. They were used for lots of financial applications for years. They're still very commonly used for like financial payment processors. Will commonly use mainframes and such. Um, I work for a local government. Um, who they use it for, again, for financial like purposes. That's mostly what they're used for, and COBOL's very good at that. It's very, very fast, very performative. Um, and yeah, I'm basically just doing programming like anyone else working a programming job would. But I also do like support for errors as they occur for these old applications because we can't just have the IT team like handle those. They require us to basically create and run like fix scripts on the mainframe to perform data fixes or fix other issues when basically the programs run into issues. Mainframes are really good with job scheduling, so you don't run into like timing issues or race conditions. At least you shouldn't really, but you can. But there's ways around that and ways to fix it. With these mainframes, do you have to create an OS custom for it or use a pre-existing? I suppose you could write a mainframe OS. I don't even know where you'd begin with that. Typically, most mainframes that you'll see in production environments will probably be IBM, probably running either ZOS, or if they're really old, they could still be on like a S360 or like, I mean, hell, even AS400s, I think, were technically mainframes. But yeah, typically you'll see most mainframes running on IBM operating systems for the one most commonly if they're running something modern, it's going to be ZOS. It's just written out like this usually. Unfortunately, IBM does not make it super easy to get experience with working on or programming for ZOS. The environment's pretty like getting a learning license. I think right now you can't even get one. They have some learning programs, but they cost quite a bit of money unless you are currently in college. I think they have actual student rates. Um, there used to be like a personal like learner's license for the actual like development environment for ZOS, but now there's not. There's just a normal like personal license, like individual license, and it's like $5,000 a year. And I'm not paying that. I am not, as much as I would love to make content for something like that, that's a little outside of what I'm comfortable spending for some educational content with my current income level. If I start making a lot more money someday, maybe I can do that. Maybe I'll do it in retirement. I don't know, but currently the pricing of the development and test environment licensing is far beyond what I'm willing to actually spend, unfortunately. I don't know if I'm sorry for rambling a bit. I don't know if I really answered your question. I hope I did. Where were we? Gonna write out the fetch function here. This feels like such a weird way to write this. This can't be right. That's how it's written here. Why? This is not like this. Non-primitive cat. Well, that'll be fine when we write that out. I'm not worried about that right now. Oh, this is not supposed to say equals 1 plus. It's supposed to be a plus. My apologies. There we go. Now it's not going to yell at me. For now. This is still angry. The reason I asked about the operating system, Lena and Cyan were going to do a Linux class, then I remember people make their own custom OS one to ask if that's something you've done before, and your job is really cool. Yeah, I think my job is really cool. I have not made my own custom OS. It is something that I kind of like think about from time to time. I think it would be really, really cool to make a custom OS. There's actually some really good resources out there for operating system development. Um, like if you just look up OS dev communities, you can find some good stuff on like GitHub, Reddit, basically wherever you're comfortable with those kinds of communities. There's some really, really cool stuff. OS development is a lot. You will learn a lot in the process, but it is unlike any other kind of development. It's not quite anything else. Oh, ad break. No. Oh, I'm sorry. Not the ads. Ugh. All right, we're gonna wait for these ads to run before we continue here too much. I don't really want to go off on too many details and lose people here just because ads are running. Yikes. Oh my. I'm always losing track of the ads. I wish I didn't have to run them at all. Like, the ideal would be to not have to run ads. That would be great. Unfortunately, I am required to. Um, just the affiliate program, you have to run at least 3 minutes of ads every hour to disable pre-rolls, and I really don't want people getting pre-rolls. Because the alternative is everyone gets pre-rolls whenever they open up the stream, and I just... I don't want people getting pre-rolls. Subscribers don't get ads, and Twitch Turbo users don't get ads. So I don't really make any money on ads. My viewers, I don't have nearly enough viewers to get money from them. I'm not really doing this to make money to begin with. But just wanted to throw that out there in case people are like, "Oh, she's running ads because of all the money." It's no. I think in the 25 something hours I've streamed so far, and however many ads I've run in that time, like probably 30 minutes worth of ads at least, I've made like less than a quarter from ads. It's like less than like 25 cents. I mean, it's nothing. We're not doing this for the ads, I promise you. All right, I think the ads should be finishing up here in like 10 seconds. Oh, head pat. Thank you. Thank you. Head pats are always nice. Okay. Looks like the ads are over. We're gonna get back into what we were doing. Oracle, was I able to answer most of what you said before before the ads cut everything out? I'm really not sure how much got cut out there. It's hard to tell sometimes. My apologies. I need to hydrate. I've been talking a lot. You heard a good amount? Okay, good. Wanted to make sure you at least heard enough of what was going on there. Good. You just redeemed another I just hydrated. I'm okay. It's okay. Everything's gonna be fine. All right. So we added our fetch function here. It's basically fetches the 16-bit opcode that's stored at the current program counter, stores this in RAM as two 8-bit values, and because basically the opcodes are stored as byte pairs. Do it again? Sure, I will drink more water if you're so insistent. I am gonna need to refill this soon. All right, let's see here. So the next thing we're gonna implement here is the timer tick. We did talk about the timer before, the delay timer and the sound timer. The delay timer just being when it hits 0, it does a thing. And when the sound timer hits 0, it plays a sound. That's just what they do. The tick function operates every CPU cycle. The timers are modified once every frame. And so they're going to be handled in a separate function. And every frame, they're just going to decrease by 1. If the sound timer is set to 1, the system will play a noise. And if they ever hit 0, they do not automatically reset. They will remain at 0 until the game manually resets them to some value. So it's basically on the game programmer to decide what they want to do with the timers for chip 8. We will write out those functions here. These are going to be exposed, so we do need the front end to be able to interact with these. So if the timer is greater than 0, we will decrement it by 1. And if the sound timer is greater than 0, same thing. We're doing a nested if block here, which is not my favorite thing in the world, but it does make sense logically for what we're doing in this case. And we decrement that by 1. So there we go. So this basically means that if this is at 1, it's going to play the beep, and then it's going to hit 0. So we're not worried about, like we did say earlier, that it technically, when it hits 0, it plays the beep. In this case, it's because this gets checked if it's at 1 after it's been decremented to 1. So it functionally is going to be working the same. It doesn't really matter in this case. So yeah. Alrighty. Looks like we're not going to go over audio in this guide. According to the author here, there's just a little bit too much complexity getting audio to work in both the desktop and browser front end for this, for WebAssembly. So we're just leaving a comment where the beep would occur. Maybe that'll be a fun little project. I can figure out how to get this to work in both desktop and WebAssembly targets and let the author know, and I can contribute that to the guide. That, that could be fun. I think that could be a little fun project. I'll make a little note for myself here that that's something I want to do. Desktop and web. We're gonna skip past that song and this one and that one. Okay, I have my little note now for that. Okay, so we have our tick timers here. I'll figure out how to make this work some other time. It could be honestly pretty fun for me, I think. Next we're going to talk about the opcode execution. So previously we added this fetch here. So, but we have not added anything for we have not added anything to make it actually do anything. And decode and execute are in some emulators, and as far as I'm aware, usually are separate. Like usually you perform them separately as their own things. For chip 8, it's easier to just perform the operation as we determine it, rather than involving another function call. So we're actually going to change this to decode and execute. And just self.execute here. Whatever the opcode that's there. And over here, we'll write that out. again, taking another mutable reference. So luckily, Rust has very robust and useful pattern matching. One of the really nice things that exists in Rust and is going to help us a lot with this. And now that I think about it, probably any other emulator when we're specifically when we're writing out the opcodes, I'd imagine anyways. So for this here, we're going to separate out each hex digit before we do any matching here. There's going to be 4 for how these are written out here. Just listen to that. This here. Unfortunately, like I said, because I decided I wanted to play some copyrighted music, we'll probably, like, this part of the VOD's gonna end up being muted, sadly. And maybe I'll get yelled at by the Twitch police if someone shows up and I'm playing it during the live stream. I think it's frowned upon to play copyrighted music during the live stream, but I think it's less of a concern if it doesn't end up in the VOD. From what I've seen in all the help documentation, so we're just not going to worry about that for right now. We're going to separate out our digits here. This should say equal. Yeah, that is what that is. We want how we do this. That's not what we want. Okay, whatever. It's fine. I know there was definitely an easier way to write this out without having, like, I could just copy and paste it, but once again, still learning these hotkeys annoyingly. Oh, actually, we're just writing this like this here. So this is not really clean. But in this case, this is going to basically allow us to create a match statement against each, because we needed all the hex digits separated here. Like we had to have this like this in order to do what we want to do. I need to space some of this out. It's bothering me. Rust format can handle what it's supposed to look like later. So now that we have that, we're going to do the following. Oh, why is this mad at me? I knew at some point I was gonna make Rust mad at me. Now I have to figure out why. This needs to be in the function. We were not supposed to write this over here. Right. I'm being silly. Nope, that needs to be there. That's there. This is here. There we go. Okay. Perfect. Whew. So Rust's match statement demands all possible options be taken into account, which is why we have this here. Which basically captures like this here, the underscores basically are just saying it's everything else. Everything that's not explicitly defined here as like an option for this match will be handled as this in this unimplemented block. Basically, this should just, I believe, panics and then prints an error, which is fine. So basically, what's going to happen is we'll add all the opcodes, and if somehow, and we need this everything else statement because there are technically other values that could exist here that Rust is going to complain about us not catching, and we're not worried about those because they should never occur. And if they do, because those opcodes don't exist in this case, and if they do, we just panic. So that's fine because it should panic because that opcode shouldn't be getting executed. So this is fine. So this is our framework here set up. So now we're going to implement the opcodes. First one, the easiest. No op. Nop. Is it supposed to be no op or nop? I would just say nop. Nop sounds funnier to me. So back in here, we're going to write our match for, oh, you know what? This needs to be indented there or it's going to bother me. And then this one, that's there. That's there. That looks better. Okay. So if it's a bunch of zeros, an extra zero there. Space this out properly. We do nothing. We're just going to return and do nothing. So we're just moving to the next opcode. Next opcode is going to be if the to clear the screen. So we want to reset our screen buffer to empty again. So we'll code that out here. And this, there we go. We write that out in hex. And we can tell this to do something on matching to that. And we're just going to say, basically set the screen back to its initialized, what it is when it's originally initialized, which should be these constants here. Oop. There we go. Next one, we're going to have a return from subroutine. We haven't talked about those yet, but it's basically we're basically moving the counter to the specified address and resuming execution from there. Um, Unlike a jump, though, like where we're basically going to a specific address, we are going back. So we're gonna have the stack here. Basically, we're gonna push our existing address onto the stack, do the routine, and then pop that value back off the stack and go back to where we were and execute from that point. This is normal stuff. So actually am going to list what these opcodes are for each one. Oops. Going to clear the screen. Clear the screen. This one will turn. Go. So to return to where we were from the subroutine, we get to this opcode. So the subroutines will have this opcode at the end of them, basically. And we're just going to have the return address be whatever was added to the stack and pop that off. And then move the counter back to the address that was stored when we went into the subroutine. Simple enough, right? Okay. Next, we're going to have a jump instruction. This is very simple. We are just jumping to the given address here. So, from what I can tell here, the way this opcode is going to work is we're basically taking, like, it's just one and then the address of where we're going. If I'm reading this correctly, if I'm understanding it correctly, which is a very good chance I'm not. It's, this is far outside my areas of expertise here, but I'm having fun learning this here. So basically, this is just going to jump to whatever comes after this here. And it's going to move our counter here to that address. So this is the most significant digit here. And the other, oh yes, so the other digits are used as parameters. The other hex digits here are the parameters of the operation. So that's why we have the placeholder here for the match statement, because we want anything starting with a 1 but ending in any 3 digits to enter this. So the only time, so any opcode that starts with a 1 will be doing this jump. They always. Next we will, this should be rather actually write out the comments here so I know what we're doing at each part of this, because I will get lost as to what the hell I even wrote at the end otherwise. I am interested in getting the sound working since the author said they couldn't. It was too complex. I'm hoping I can do it in a way that's really nice and easy. It doesn't require anything crazy with like external crates. I'd like to get it to work on both desktop and WebAssembly targets, since that's what this guide is for. Needs more water there. Alrighty. Whew. So this next one here is basically if we, let me get rid of that. There we go. Okay. Yeah, we'll listen to that. Always love covers. This is similar to the last one. Instead of a jump, though, we are basically going to go into a subroutine. And this is any opcode that comes in here that starts with the 2. So this is going to push the return value of wherever the counter currently is. It's going to push that onto the stack so that we have our return. Because here we pop that back off. So this is perfect. This is exactly what we want here. How many opcodes do we actually have in this? So we're actually pretty far into this, believe it or not. Okay, we have quite a few opcodes to implement here. So we'll get through that here, and then it looks like all we have to do after that is to write the front end. So back to our lovely little guide here. This is where we are. Perfect. Okay. Run equals here. There we go. Okay, so the way this works, this is basically saying if this is basically being able to skip a line. It's kind of like an if else block. So this is going to allow us to skip a line. So we make a comparison. If it's true, we go to one instruction. If false, go somewhere else. So this is using one of our V registers here. So the second digit tells us which register to use, and the last two digits provide the raw value, is what's happening here. So this is going to tell us which register to use, which V register we're using, and then these two here are are oh my gosh, my brain's not working. The what's being checked. Whew. And then we just increment the counter by 2 if it matches, and that skips a line. So basically, instead of doing the next, whatever the next thing is, we're going to the one after. So it's like an if-else block, basically. Whew. I do not know how people at stream talk all day. My throat is so dry. Drinking plenty of water here. It still feels like it's too much. All right. So this is just going to be similar to a lot of these next ones, it looks like. So this is a skip. The next one's another type of skip. We're not too worried about this. It's nice and easy. Head pad. Oh, thank you. Thank you. Pets are so nice. That needs a comment. There we go. So 4. This just checks to see if it's not equal. Okay. I'm probably going to just copy the rest of these opcode blocks in. And if there's anything I don't understand, I like to type things out because it's a little easier. But the rest of these are just more skip, skip, skip. It's just we're just checking values in the registers and skipping if we match on certain conditions. It's basically just implementing kind of like if checks, but in different ways, because assembly works in a very interesting way. Oh. Oh my gosh. Come on. Oh, come on, you. That one. And okay. This one's just setting the V register by the second digit to the value given. Like I said, I just didn't feel like writing all these out by hand at the moment. I apologize if that you all wanted to see me do that. I think you'd have to be a little crazy. I'd much rather save myself the time and the unneeded effort by just doing it this way. Because we already know what we're doing here. This is just, so here we're just setting the V register. These were basically if blocks here, the 3, 4, and 5. This one is basically adding a value to the, adding a given value to the VX register. And we need to make sure this doesn't overflow, which is why we have this wrapping add here. Because if it overflows, Rust panics, and we don't want that. Chip 8 has a carry flag, but it's not modified by this operation, so we have to implement wrap here ourselves. Change the music again here. Thank you everyone who's here hanging out. It's been interesting so far, at least for me. I'm having a good time. Like I said, at this point we are, unfortunately, just copy and pasting a few blocks. It's just save quite a bit of time. Because doing this out manually would be nightmarish. So this one is like here, but instead of setting it to whatever was passed in, we're just oh my gosh. Instead of setting the register to whatever the value is here, we are setting it to, we're setting the vreg here to whatever was in y, vx2 vy. Quite a few more opcodes to paste in here. You'll bear with me a moment. Quite a few. In fact, most of the rest of this is just implementing the opcodes. I am thinking I have a pretty good idea of how this is all working at this point. I mean, we were doing this for educational purposes. I'm not sure we're going to go to completion with this project. There's no real reason to. I mean, again, we are following directly from a book, so going to completion here doesn't really do anything for us. Other than we could just say it's fun. In this case, I am thinking, based on what I'm reading here for what's going to be used for the rest of this, I'll probably put this off, do the rest of this off stream. Some of this is going to be used with like STL to actually draw the window in the canvas, or it's going to make the window and then give us a canvas that we're going to draw on. But I am not in the headspace to probably finish this out here. I'm thinking my throat is killing me. I'm not sure if it's because of all the talking I did the last couple of days or what's going on, but I can tell you right now, it doesn't exactly feel the best. So, with that in mind, I'm going to give myself a little bit of rest here. We will do another stream later in the week. I'm thinking probably maybe like Wednesday night, Wednesday or Thursday, something around there, for like another couple hours. Probably something comfy. I might stream again later today, but I absolutely need to give my voice a rest right now. It is not doing well. I'm sure some of you who know what I usually sound like can definitely hear it straining a little bit here. So, thank you everyone for coming out. We'll be ending the stream here, and I'll see y'all next time. Hopefully, I can get Twitch to stop yelling at me about the bitrate. It's supposed to be max 6,000. It's at 6,000, and it's just telling me it's too much because it's 5 kilobytes over 6,000. So I'm gonna have to like clamp it to like 5,900 or something in OBS in the future. It's just a little annoying, but it is what it is. All right, I hope y'all